Okay, so last lesson we had a revision for the reactions related to alkanes and alkenes, and I have checked your homework. So for checkpoint questions related to alkenes, students who have submitted the work show no problem, so I will just skip that part. So this week we mainly focus on the reactions related to haloalkanes and some reactions related to alcohols, because you can see it's quite a long sections in this unit. Okay, so today we begin with reactions related to haloalkanes first. So haloalkanes, first you need to recognize the structures. So one of the hydrogen, or it can be more, but one of the hydrogen must be replaced by an halogen. So this X can be chlorine, can be chlorine, can be bromine, or can be iodine. Okay, and the key reactions you need to remember for haloalkane is substitution reaction with alcohol. With alkaline condition to produce alcohol. Okay, so it's a reaction that converts haloalkane to alcohol. And the condition you need to remember first, it must be conducted under alkaline condition. Okay, so that's why we have OH minus. Okay, state is alkaline condition, and also in aqueous state, that means water is presented here. And this reaction would not undergo at room temperature, so it needs to be conducted while heating under reflux. So later we are going to look at this setup because you will be assessed how to do this kind of experiment. Okay, so first take a look by reading the name, substitution reaction. Okay, that means we are going to substitute this halogen in the haloalkane with an OH group to form alcohol. So if we look at some example here, for example, the first one is bromopropane. Okay, so while reflux under alkaline aqueous solution, then the bromine, okay, here will be replaced by an OH group and form an alcohol. Okay, so we could write the product. Okay, and it should be this one. Okay, so produce an alcohol. And what's left? Okay, so this OH group is actually comes from the water. Remember, water dissociate readily to form H plus and OH minus. So the OH minus will replace the bromine, and then left with the H plus, and the H plus would join the bromine ion, left haloalkane, and produce the other product. And the mechanism we're going to discuss in detail on the next page. Okay, so for this stage, I just want you to be able to work out the product first. Okay, so that's the first example. Very easy. How about the next one? Next one, we have this chlorine. Okay, so again, under alkaline condition in aqueous solution, we heat it under reflux. The chlorine will be replaced by an OH group. Okay, so we can write the product. So remember, there are two ways to draw the benzene ring. You can draw 3 double bonds, or you can just draw a circle in the middle. Okay, both will be accepted. Okay, so remember here, the OH replace the chlorine. Okay, and the other product we have should be the hydrogen ion left in the solution to join with the chlorine ion that left the haloalkane. Okay, so these are the two products from this reaction. So for general reaction or chemical equation, you should have this one: haloalkane plus the water will be split into H plus and OH minus. The OH minus will replace the position of the halogens at the beginning, and the hydrogen will join with a halide ion. Okay, So take a look at some important things you need to jot down for this reaction. First, this alkaline condition here, the OH minus, usually we use sodium hydroxide or potassium hydroxide, and they are catalysts. Okay, so they are only used here to provide an alkaline medium, and it is not consumed. So they act as catalyst. Okay, and for this reaction, we must add the catalyst. Otherwise, the reaction won't start. Okay, and the second thing you need to note is that the physical state, AQ. Okay, so that means it provides the water for the reaction. So if we put it in organic solvent, other type of reaction would take place, and you will have a mixture of the product. So not the alcohol that we want. Okay, so here, make sure you have written down AQ to show that water is here for the reaction. And the next one, why we don't write heating, or why we need a special setup called the reflux. Okay, imagine this. Okay, we have these two reactants, and now we got the alkaline conditions with water in it. Without heating, there will be no reaction. But as we started to heat it, remember here, the haloalkane, it got no OH group in it, okay? And it only have weak van der Waals forces between the molecules. Okay. Yes, if I go too quick, make sure you remind me to slow down. Okay, so now, after we put in the two reactants, and we make sure we have the catalyst and the correct condition, then we start to warm it. And remember, for haloalkane, it cannot form any hydrogen bond. So only weak van der Waals forces will be found between the molecules. That indicates the boiling point for haloalkane is pretty low. Okay, so while we start to heat it, it's gonna evaporate readily. Okay, even quicker than water. Okay, because between water molecule we have hydrogen bond. So when we start to heat it, the organic reactant gonna evaporate. Hence, there will be less or no haloalkane in the container to react with water. So we won't have any product. So how can we deal with that problem? For example, at the beginning, we got the Bunsen burner to heat it, okay? As we start to heat it, the organic reactant gonna start to evaporate and escape the system. Okay, so it won't have any reactions here. So how can we stop that? How can we stop the organic solvent to escape from the system? We cannot remove the heat, otherwise the reaction won't take place. But can we simply add a lid here to cover it? Will it cause any problem? So if I add a lid onto it, yes, it can block the haloalkane to escape the system, but it will build up the pressure inside your container because it's closed. Okay, the evaporated haloalkane will stay in the container, build up the pressure, and it may explode in this case. So this is not a practical way to solve the problem. So we designed a special setup called reflux to solve this problem, okay? To deal with something that has a low boiling point, but we want to keep it in the container for reaction. So let's move on to page 12 to talk about the experimental setup first. Okay, so now you can see this is an experimental setup. Okay, and for this setup, we can call it reflux, or sometimes we refer it as heating under reflux. Okay, so now here we got a container. Sorry. Okay, and inside the container. Sorry, I can't hear you.
第10張係點樣㗎？係咪仲上面有㗎？
What? Hello?
唔係啊，佢應該係佢阿媽講緊嘢，跟住佢唔小心撳咗 unmute， 所以咁。完咗未？定係 pending 喺度？
我就睇第11版10版啊。
Okay, I have to mute you, I'm afraid. Okay, let's carry on. So at the bottom, we have this container to keep those two reactants. So we need to have the haloalkane and together with the aqueous solution. And we have sodium hydroxide as a catalyst to start the reaction. And also, we're going to heat the two reactants. Sorry. Okay, and the reaction gonna take place and some of the haloalkane would evaporate. But here, the special part for this setup is that we have a reflux condenser, okay, near the tube of this setup. So what's that for? Okay, you can tell by its name, condenser. So we have usually the round cold tap water going in from the bottom, so it will make sure the cold running water will fill the whole tube, surround the whole tube, and then goes out on top. Okay, so this is to ensure that the tube's temperature remains quite low. So as soon as the haloalkane evaporates and touch the wall of this tube, it will condense back to liquid and then drop down to the container at the bottom. Okay, so the haloalkane evaporated but would not escape, or most of them would not escape, because it will condense back to liquid and drop down. Okay, so that's the purpose of this setup. And the key parts I want you to highlight on your notes. Make sure this container is left open. Don't put a stopper on top. Otherwise, it would just be the same as a setup I drew on page 9 here. Okay, it become a closed system, and the pressure would build up in your closed system, so the whole thing would fail. Okay, so remember, for reflux, leave the top part open. Do not put a stopper on it. And one more thing I need to mention for the reflux. So here, remember, water needs to come in from the bottom and comes out at the top. Why is that? Okay, so I have found a photo to show you. Okay, so if we take a look at this, if we fill the water from the top, the water would just, okay, fall down and then leave the reflux condenser. It would not fill the whole tube, the whole condenser. Okay, so some part of the condenser would be left empty. Hence, if the haloalkane evaporate and touch this side of the condenser, it would not condense back to liquid. It would just escape the system. But if we do it the other way, if we let the water to enter in from the bottom and to only let it to leave on top, that will make sure the water will fill the whole tube, the whole condenser. Okay, hence haloalkane evaporator touch any part of the condenser, it will condense back to liquid and drop down. Okay, so two things you need to highlight for this part. Okay, then open end and also the direction of the water we put it in. Okay, so here to start for this one, you will be assessed for the experimental setup for this. And I have found a video to quickly show you how reflux have been done in the lab.
Firstly, clamp your condenser to the retort stand. Connect the rubber tubing from the bottom of the condenser to the top. Turn the tap on gently and make sure there's a constant flow of water going through the tubing, through the condenser, and back into the sink. Move the hot plate stirrer and sandbag into place, and connect the round bottom flask onto the bottom of the condenser using a green clip. Carefully lower the clamp on the retort stand so the bottom of the round bottom flask is touching the sand. Turn on the heat and keep the solution stirred. It will take up to 5 minutes for the solvent to start refluxing. The point of reflux is when the solvent is evaporated, reaches the condenser, and starts dripping back down into the round bottom flask. Watch the reaction carefully, as you need to know when to start timing your reflux. When the reaction is finished, turn off your heating mantle. Using the clamp, raise your condenser and round bottom flask out of the sandbag. Let the round bottom flask cool down before touching it. Once cooled, remove the round bottom flask from the condenser and always remember to turn off the heat.
Okay, so that's for the heating on the reflux part. Okay, so now we know how we do this experiment. The next part, we need to work out how this whole thing works. So the mechanism. Okay, so for the mechanism, okay, remember previously we have learned nucleophilic addition. Okay, so here I'm going to introduce two new terms. So first, it's called a nucleophile. Okay, so what is a nucleophile? A nucleophile can be negative ions, for example, hydroxide ion or cyanide ion, and compounds, for example, ammonia, in which an atom has an unshared pair of electrons. Okay, so like a lone pair of electrons. So they can work as nucleophile. And because they have those unshared pair of electrons, they will be able to potentially donate those electrons. So it would attack the center of positive charge or partially positive charge. Okay, and that's for nucleophile. And for nucleophile, sometimes when you look at the mechanism, it might be represented by Nu. Okay, if it got a charge, then it's gonna be Nu minus. Okay, so that's for nucleophile. And then the second term you need to remember is a nucleophilic substitution reaction. So for short, we write SN reaction. Substitution and a subscript of capital N to represent its nucleophilic. Okay, and for this kind of reaction, a nucleophile selectively bonds or attacks a positive or partially positive charge of an atom or a group of atoms to replace a leaving group. Okay, that's why it's called substitution. So basically, the nucleophile substitutes the leaving group in a reaction. Okay, and for nucleophilic substitution, it would undergo two different ways. Okay, so here is a very simple representation to let you know the difference. Okay, so in this diagram or in, okay, so you got two cats. Okay, so this cat is a nucleophile. So it will eventually replace the leaving group. Okay, so at the beginning and the end product, they're the same, but it goes through two different ways. What are the difference? If you take a look at the middle part, okay, so the middle part represents the reactive intermediate. So in the first one, the reactive intermediate is formed here. So only one molecule is involved in forming this reactive intermediate. Okay, this nucleophile just sit there and watching, it did nothing. Okay, but for the second one, okay, you can see it's due to the orange cat that coming in that pushes the gray cat out. Okay, so to form this reactive intermediate, it involves two molecules to participate in this part, in this stage. Okay, so that's the difference. So if it only involves one of the molecule in forming the reactive intermediate, then we call it an SN1 reaction. Okay, if it involves two molecules to form the reactive intermediate, then we call it SN2 reaction. Okay, so let's take a look at SN1 reaction or SN1 method first. So for SN1, this mechanism is taken by tertiary haloalkane. Okay, so what's going to happen is the leaving group will leave first. Okay, and it left with this reactive intermediate, which is a carbocation. And for this carbocation, remember the alkyl group, okay, can stabilize the carbocation, okay, by what we call the inductive effect. So we mentioned that in unit 27. Okay, so this alkyl group, they can kind of like donating the electrons towards the central positively charged carbon. Okay, so that it would stabilize this carbocation, make it less positive. And then that's the first step. Okay, it happens stepwise. And in the second step, remember we have OH minus in the aqueous solution. So the OH minus, because it has a lone pair on it, it has a unshared electrons. So it acts as a nucleophile. So the nucleophile would attack the positive side of the molecule. Okay, would attack the carbocation. And then it will form this product. So if we compare the product with the previous starting molecule, you can see hydroxide have replaced the position of this chlorine. Okay, so that's for SN1 reaction. So only one molecule involved to form the intermediate. So it's called SN1. Okay, and then let's take a look at the other route. So for primary and secondary haloalkane, it will undergo a different mechanism. So here, unlike the first stage, unlike SN1, the bromine would not leave immediately, but the nucleophile gonna attack the central carbon first because the central carbon got a partial charge on it. Okay, and then it will form this transition state. This is very unstable, okay, because these two bonds here, we say it's half made and half broken. Okay, so the nucleophile attack the carbon to form this bond, and because there is a bond between the hydroxyl group and the carbon, so this newly formed bond weakens the bond between carbon and bromine. okay? And this transition state molecule is very unstable. Okay, and this transition state is very unstable. So eventually, the bromine gonna leave as bromide ion. Okay, so in this mechanism, you can see there are two reactants involved in forming this reactive intermediate. Hence, it's SN2 reaction. Okay, two species are needed. So we call it SN2. Okay, so when the nucleophile attack the partially charged carbon here, it will push these three groups to a different position. Okay, it's gonna repel us. So it's gonna form this structure we have learned is the trigonal bipyramidal. Okay, and then as the CBr bond is weakened, then the bromine gonna leave eventually as a bromide ion. Okay, so remember, primary and secondary haloalkane would prefer to go through this SN2 mechanism. Okay, so some of you might ask, why can't the primary or secondary haloalkane go through the SN1 mechanism? Like this. Why? In this case, the bromine will not just leave the molecule. Okay, so that's due to the inductive effect we have mentioned before. Okay, so here I show you the example here. That's a primary haloalkane. So this carbon that directly bonded to the bromine bonded with an alkyl group, the carbon chain, and two hydrogen here. So that's primary haloalkane. So if this bromine just leave and form the bromide ion, this carbocation would have one hydrogen here, one hydrogen here, and then the carbon, the positively charged carbon would not be stabilized by the alkyl group. So only one methyl group here. There's no methyl group at this position or this position that try to donate electrons towards this positively charged carbon in the center. So this positively charged carbon is not stabilized. It's very unstable and much more difficult to produce. Okay, so this way is not preferred. It requires much more energy input, and this one is really hard to produce. Hence, it will go through another way that requires less energy input. It will go through this transition state. Okay, so any question for this part? Because this is quite new and quite complex concept that you need to know. Okay, so any question about SN1 and SN2 mechanism so far?
你可唔可以講多次啊？
You mean the whole thing?
唔係啊，即係嗰個第11版同埋係咯，第11版。
This part? SN2. Okay, so for this one, as I have mentioned, the primary haloalkane, okay, it got this kind of structure. So if it undergo SN1, so we expect this bromine to leave directly, okay, and then it will form a bromide ion and then the carbocation. But for this carbocation, since it only have one alkyl group next to it, so only this alkyl group can kind of donating the electron towards the central positively charged carbon. Okay, the hydrogen would not be able to do so. So it would be less stable if we compare to this one. Okay, if we have a tertiary haloalkane, you can see there are 3 methyl groups surrounded by this positively charged carbon. So all these 3 methyl groups will be able to kind of donate its electron towards this carbon. Okay, hence it would make it less positively charged. Okay, so more stable. But this one, since it mixing 2 alkyl group, it's much more unstable and much more difficult to produce. Okay, so this method is not preferred by primary and secondary haloalkane. Okay, this is very unstable. Then instead, it will undergo a mechanism called SN2. So instead of breaking the bond immediately, it will go through a transition state. Okay, so the nucleophile again attacks a partially positively charged carbon, okay, because bromine is more electronegative. And then it will form a new bond with this carbon. So between the hydroxyl group and the carbon, it will form this half-made bond in the transition state. And also, because we have a half-made bond, it weakens the carbon-bromine bond. So this is a half-broken bond. And through the transition stage, it will eventually break. So the carbon-bromine, the bond becomes too weak and the bromine gonna leave as a bromide ion. So it will undergo this SN2 reaction, SN2 mechanism instead for primary and secondary haloalkane. Okay, so if we back to this simple representation, you can write down this is a SN1 mechanism and this is a SN2 mechanism. Okay. Okay, because we have a catalyst to push this reaction, we want to form the alcohol by doing this reaction. Okay, so this reaction, why we need to talk about it? Because this reaction is one of the way to produce alcohol. Okay, so you can write this down. Okay, so sorry, alcohol preparation. Wrong word. Ouch. Okay, so by doing this, we can prepare alcohols we need. And later on, we're going to talk about the second reaction to prepare alcohol, but in later sections next week. Okay, so as you can see, in this reaction, it involves water to dissociate to form H plus and OH minus. Okay, hence water, okay, is split into these 2 parts in the process. Then we call it hydrolysis. Okay, hydrolysis. Hydro means water. I think the ending part means separating it. Okay, so if I ask you what kind of reaction is this, like the checkpoint question 1, what type of reaction occurs? So for this one, okay, you can either refer as hydrolysis or nucleophilic substitution reaction, both of them. okay, will be accepted. Okay, so any question for now for the haloalkane part? Okay, for the mechanism part, if you're still a little bit struggle with, then you can replay the video later on. Okay. Okay, I think we're fine for today. I think I've gone through a very important concept, so I think we will be okay to end now. So if you got any questions, you can stay behind and ask me. For this one, you need to state is nucleophilic substitution. Okay, that's required in IFY syllabus. You need to have that nucleophilic keywords in it. Okay, so it's either hydrolysis or nucleophilic substitution reaction. Okay, and I'll see you tomorrow. And tomorrow I would like to go through Unit 30 exercise with you, and I will try to return your work by today or early tomorrow. And if we have time, we're gonna move on to the alcohol part. Okay? And again, try to attempt the checkpoint question uploaded onto Google Classroom.